Good evening, sir. You can get them in it.
How many events are in
Six. In this one is six.
a butterfly calendar? What are your box to
It's just students. Just students. Students are away. You can fix it back.
your time?
No time.
Um,
You look at this me. Yeah.
no time?
Is someone sleep before?
No. Then it's based on the, but you have done 60 back the chore.
Yeah, but we did not produce units.
Oh, so don't do it for the views. And
Good afternoon, sir. Good afternoon, Asia.
Afternoon, man.
so
Yes, Mackie, here you soon come. All right, guys. I was hoping that others would have joined pretty soon so we can have Asia needs somebody to present, so Asia can't just present to me. So when we can call Carol and Paz and see. By the way, what happened to Paz? I've not seen, he wasn't there on Tuesday. See if we can call him, please, because I want to wrap up the atmosphere today, but I also want to give Asia an opportunity to present, and then we can start the hydrosphere. So, sorry, we did the hydrosphere. I want to start the atmosphere today. So,
Okay. Okay.
right. So, see if we can just call. I was in some noise a while ago, so I am actually walking away from the noise. And as soon as I get settled in, meaning I find my sit down alone seat, I'm going to be starting. So in another 3 minutes thereabout, or call it 5. All right. So see if we can call the guys in the meantime for me, please. In terms of reaching. All right. Any luck in finding them?
No, sir.
Mm. Mm. All right. The show must go on, though, because I not went to sit and wait on them because they don't even message me and say, boys, so we're not coming. So I know exactly what is what. All right. I will still give Asia the opportunity to do a presentation. What did I'm just trying to remember what did um But the current present on different. The present on her thing was on acid rain, don't?
Yes, sir.
So that means she's kind of the atmosphere. What was yours again, Michael?
BOD, COD,
Okay, BOD, COD. What is yours,
yeah.
Asia?
Sir, this is also done using natural water.
All right, let me just click on something quickly and then. Wait. Which of you using a computer today?
I am.
Good. Um, I'm in no drama with this setup of mine, so. Monday, my class. Where's the line? What's in the message? Mm, 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 mm. All right, let me see. I need to find. I need to look at the old thing. Environmental. Seriously, and the environment. So we look at the hydrosphere. Hydrosphere. We looked at the water cycle, right?
Yes, sir.
Mm, right. All right. So we pretty much finishing off the hydrosphere, and then I want to look at the. I want to look at the. I want to introduce the atmosphere to you tonight. Um, just to give an overview, and then again, I want to have a conversation maybe on it, and then I'm going to give you an opportunity to research and present as well. Just here, environmental policies. All right, so. All right. All right, so let me just give a quick overview. No, so the overview, not, you know, allow Asia to speak first, and then I do the overview of the. Asia, I'll allow you to speak first before I go into the hydrosphere. I was going to go through the overview, but let me allow you to speak. Go ahead and share and do your stuff, Mom. We're not waiting on the rest of them. Let's go.
Okay, sir. 1 second.
Mhm. Mhm.
Okay, good evening, everyone. So my presentation this evening will be focusing on the nature, sources, and types of dissolved substances in natural water. So firstly, what is natural water? So it can be defined as water that occurs in a real world environment or an environment that is, as we say, natural from nature, such as lakes, streams, or groundwater bodies, as opposed to like synthetic solutions in a lab, for example. So first we will start with the nature of dissolved substances in natural water. The nature of dissolved substances in natural water is fundamentally tied to the properties of water itself, particularly its polarity. So for this portion of the nature, we'll be focusing on water's ability to act as a universal solvent, well, though not entirely, as it stems from its polar nature. Next, the polarity facilitates interactions with a wide range of substances, allowing them to dissolve, and then the process of dissolving involves water molecules surrounding and dispersing some water. So water's polarity. According to ChemTalk, by definition, a polar molecule has a partially positive end and a partially negative end. The molecule achieves this by having an uneven distribution of electrons between its atoms. That is, electrons gather more closely to one atom than the other, thus making one atom slightly more negative than the other. Moreover, these atoms must also be arranged in a way that their partial changes do not cancel each other out. So as stated above, to be polar, a molecule must actually have polar covalent bonds and also be asymmetrical. So water has a bend structure, which makes it asymmetrical, as you can see in this diagram here. So it's asymmetrical and it has a bend structure and has OH bonds where the O end is partially negative and the H end is partially positive. So the image here shows a water molecule, as you can see, with its electrostatic potential map. And the map reveals that the oxygen atom has a negative charge, which can be identified by the red aura around it, while the hydrogen atoms have more of a positive charge, which is identified by the blue around it. And this uneven charge distribution makes a polar molecule itself, explaining its ability to actually dissolve many substances, which actually adds to its high boiling point. So water molecules have a unique structure. Oxygen atom attracts electrons more strongly than the hydrogen atoms, resulting in a partial negative charge on the oxygen and partially positive charge on the hydrogens. This uneven distribution of charges makes a water a polar molecule. This polarity is crucial because it allows water to interact with and dissolve many other substances. So the role of solvation. Solvation is another one of our nature, another one of our properties. So solvation in water, also known as hydration, is the interaction of a solvent with the dissolved solute. So we know the solvent and the solute different. The solute, the one that being dissolved, and the solvent is the one that does the dissolving, basically. It occurs when the intermolecular forces between the solvent and solute particles are more significant than the intermolecular forces holding the solute particles together. So in this image below, which is a depiction of the solvation process, so it shows how polar solvent molecules like water dissolve solute ion. So the solute molecules surround the ions with their positive ends, attracted to the negative ions and their negative end attracted to the positive ion. So positive, negative, and they're attracting each other. This stabilizes the ion effectively, leading to like this dissolving, basically. When a substance dissolves in water, water molecules surround the individual particles, ions or molecules of the substance. This process is called solvation, as we discussed, which is also hydration. For ionic compounds like salts, water molecules separate the ions from the crystal lattice. These positively charged ends of water molecules attract negative ions, and the negatively charged ends attract positive ions, as we discussed earlier. This effectively pulls the ions into solution. For polar molecules, water molecules form hydrogen bonds with the solute, which helps to disperse the solute throughout the water. Next, we have another property, which is the type of interaction. So ionic interactions is the first one, which is also known as ionization. So these interactions occur when water dissolves ionic compounds. Electrostatic attraction between water molecules and ions breaks the ionic bonds in the solute. When an ionic compound, for example, sodium chloride or NaCl, is placed in water, the water molecule surrounds the individual sodium and chlorine ions, and this solvation or hydration process actually weakens the ionic bonds, holding the crystal together. The ions disperse throughout the water, and this is the primary interaction responsible for the dissolution of salts and other ionic compounds in water. So those who don't know what dissolution is basically the process of creating a solution. So for this section, I myself would imagine it being like, imagine dissolving salt in water. So the water molecules are like tiny magnets that actually pull the salt apart, if you can imagine that. So the positive end of the water molecule sticks to the negative parts of the salt, and the negative end of the water sticks to the positive parts of the salt, and vice versa. And this keeps the salt broken up in the water. And basically that's what happens when any ionic compound dissolves in water. Next we have hydrogen bonding, and this occurs when water dissolves polar molecules. Hydrogen bonds form between water molecules and the solute, allowing the solute to disperse. Polar molecules have an uneven distribution of electron density, resulting in partial positive and partial and negative charges. Water itself forms extensive hydrogen bonds with other water molecules. The partially charged regions of the polar solute molecule attract with the partially charged regions of water molecules forming hydrogen bonds. These bonds help to disperse the solute molecules through the water as the water molecules surround and interact with the solute. So for example, sugar molecules have many OH groups, which can form hydrogen bonds in water, why sugar readily dissolves in the water. And as a result, the polar molecule dissolves, forming a solution. So another analogy, sugar, as we said, sugar molecules have parts that are slightly positive and slightly negative, like our tiny magnets, as we established before. Water molecules are also like the tiny magnets, and the positive parts of the water stick to the negative parts of the sugar, and then vice versa as well. This allows the water to surround the sugar and spread them out, essentially making the sugar dissolve. And that's basically how water dissolves anything with these polar molecules. They just stick together basically and then they spread out, in a sense. That's a basic way of looking at it. Dissolving gases is another interaction. So gases like oxygen and carbon dioxide dissolve in water through physical processes. The amount of gas that dissolves depends on factors, for example, our temperature and our pressure. Gases consist of molecules that are widely separated and in constant motion. Gas molecules dissolve in water through a physical process, not a chemical reaction in most cases. CO2 reacts with water, but that is a special case. Gas molecules occupy spaces between water molecules, interacting through weak intermolecular forces. Lower temperatures increase gas solubility because gas molecules have less kinetic energy and are more readily trapped by water molecules. An example of this would be our oxygen from the atmosphere dissolving in water, providing oxygen for aquatic life like fish in a pond and so on. Carbon dioxide dissolves in water, forming carbonic acid, which is H2CO3, which contributes to the acidity of water. The result is the gas dissolving, forming a solution, and the amount of gas dissolved is influenced by the environmental condition. So, separate from imagining the pond with the water, we can think of imagining a glass of soda. The gas molecules squeeze in between the water molecules, basically. So more gas can fit in the cold soda because the gas molecules move slower, or you can say, and are more easily trapped by the water. But when it gets warm, the gases move faster and escape the water. So that's why warm soda goes flat faster. It's like the water is holding onto the gas, and how much it can hold depends on, as we said, our temperature, for example. And now we have our dynamic equilibrium, which is another nature. So we'll finish with our types of interactions. Now moving on to dynamic equilibrium. The dissolving is often a dynamic process in a saturated solution. The rate of dissolving is equal to the rate of precipitation. This means that even though a substance is dissolved, there's a constant exchange of particles between the dissolved and the undissolved states. So dynamic equilibrium is not a static condition where everything stops. Instead, it's a state where two opposing processes occur at the same time. This results in no net change in the overall concentration of the dissolved substance. Dynamic emphasizes the process are ongoing. So for example, in a saturated solution, solute particles are constantly dissolving and precipitating, but the amount of dissolved solute remains constant. Dynamic equilibrium applies to reversible processes, meaning they can proceed in both directions. In the case of this solution, it means that the substance can both dissolve and precipitate out of the solution. Saturated solution is a prime example. When you add a solute to a solvent, it dissolves until it reaches a point where no more solute can dissolve at that temperature. At this point, the rate of dissolution equals the rate of precipitation. Even though the concentration of the dissolved substance remains constant, individual solute particles are still constantly moving between the dissolved and undissolved states. So again, with our salt and our water, initially the salt dissolves rapidly, and as the concentration of the salt increases, the rate of precipitation also increases. Next, on to our sources. One source is our atmospheric, which can be separated into our dissolved gases and aerosols and dust. So as rainwater descends, it naturally absorbs gases from the atmosphere. CO2 is a significant component, forming weak carbonic acid, which influences the water's pH. Oxygen and nitrogen also dissolves, with oxygen being crucial for aquatic life. Atmosphere itself, with gas concentrations influenced by biological activity, volcanic emissions, and human activities, such as fossil fuel combustion and more. Now our aerosols and our dust. So atmospheric particles, including our dust, our pollen, and sea salt aerosols can dissolve in rainwater. These contribute minerals and other substances to water bodies. Some sources include our wind erosion, volcanic eruptions, sea spray, and our industrial emissions. Next, we have our geological sources. So rock and salt weathering is one, where water flowing over and through rocks and soil dissolves minerals through chemical weathering. Type and concentration of dissolved minerals depend on the geological composition of the area. So some examples of this may include limestone dissolution, which releases calcium and bicarbonate ions. So imagine a stream flowing over limestone rocks. The slightly acidic rainwater slowly dissolves the limestone, like we can say, like our salt in water, or sugar in our tea. This releases calcium and bicarbonate ions into the water, making it essentially hard water, as they say. Next, we have weathering of silicate rocks, releasing silica, sodium, and potassium ions. So thinking of granite, a common silky rock, rainwater, especially with a little acid from the air, slowly breaks down these rocks, and this releases things like silica, sodium, and potassium in the water. When we have contact with sulfide minerals, can release sulfate and trace metals. These minerals often contain metals. When water flows through them, it can cut the sulfate, trace minerals, or metals, sorry, sometimes making the water taste metallic or having a distinct smell. If we have our groundwater, due to its prolonged contact with subsurface materials, often has a higher concentration of dissolved minerals than surface water. So, as we can imagine, groundwater as water that has been soaking in the earth for a very long time, like before us, before our grandparents. Because it spends so much time in contact with like our rocks and our minerals underground, it has more time to dissolve them, leading to a higher mineral content. This is why well water often tastes much different than surface water. And then our last geological source is our mineral deposits. So water entering mineral deposits, encountering mineral deposits such as salt deposits, readily dissolves these substances, leading to high concentrations of specific ions like our sodium and our chloride. Some sources are naturally occurring mineral veins like our quartz, our sulfide, our carbonate veins. And our deposits, salt, limestone, and metal ore deposits. So our naturally occurring mineral veins are fractures in rocks filled with mineral deposits, you can say. They form when mineral-rich fluids circulate through the cracks and the fissures, depositing minerals as they cool or as they react with the surrounding rock. And for our deposits, some examples, we said our quartz, veins, the sulfide, the carbonate. And the quartz veins often carry gold and silver. We have our sulfide veins like pyrite, galena, and others, and our carbonate veins, which is composed of our calcite and our dolomite. Then we have our biological sources, which composes of our organic matter decomposition and the metabolic processes. So the breakdown of organic matter, such as decaying plant and animal material, releases the dissolved organic carbon, nutrients, and phosphorus, and other organic compounds. Some of these sources may include decaying vegetation, animal waste, and microbial activity. And we have our metabolic processes. Our aquatic organisms release dissolved substances through their metabolic waste, our processes, including excretion and respiration. And these can come from all living things within the water source. Next are human-caused sources. So agricultural runoff, industrial discharge, we have sewage discharge, urban runoff, among others. So for these four, agricultural runoff, we have fertilizers, pesticides, herbicides applied to agricultural lands can be carried by runoff into water bodies, basically introducing nutrients like our nitrates and our phosphates and potentially harmful chemicals. Some of these sources may include like farming practices such as fertilizer application, pesticide and herbicide use, irrigation, livestock management, tilling, and so on. Industrial, these can be released by a wide range of dissolved substances like heavy metals, organic chemicals, and other pollutants. And these can come from factories, mines. We have industrial processes which can release wastewater, accidental spills. We have drainage from the mines, leaching, and so on. For sewage, which is untreated or poorly treated sewage, introduces organic matter, nutrients, pathogens, and pharmaceuticals into water bodies. And this can be from residential and commercial wastewater. And finally, our urban runoff, which is rainwater that flows over urban areas, can pick up many pollutants. This includes our road salts, oils, heavy metals, and other chemicals. And these can come from city streets, parking lots, and construction sites. For our last heading are types of dissolved substances, which include inorganic substances such as our ions and our dissolved gases or minerals, organic substances, and so on. So starting with our ions, which are our cations and our anions. Cations we know are positively charged, anions are negatively charged. And some of these cations include calcium, magnesium, sodium, potassium, and iron. Now, calcium can come from limestone and other materials or minerals. Magnesium from minerals like dolomite. Sodium from salt deposits and the weathering of rock. Potassium from the weathering of silicate rocks. And iron from iron-containing minerals. Anions, we have our chlorides from salt deposits, sulfates from sulfide minerals and gypsum, bicarbonate from dissolution of CO2 and carbonate rocks. We have our nitrates from atmospheric deposition and agricultural runoff, and the phosphate from fertilizers as well. Dissolved gases, we have our oxygen, which you know is essential for aquatic life. CO2 actually forms carbonic acid, which influences the pH of the water. Nitrogen, a relatively inert gas. And next are minerals. So silicate or silica from the weathering of silicate rock. Organic substances, which are dissolved organic matter or DOM, which may include humic substances from the decomposition of plant matter, organic acids, which are various compounds from biological processes, and are pesticides and herbicides from agriculture. And then nutrients, dissolved organic nitrogen and phosphorus, essential for plant growth, but excessive amounts can lead to eutrophication, which you know a lot about. And lastly are microorganisms, which not strictly dissolved in the same way as ions or gases. Natural water contains a wide range of microorganisms, such as our bacteria, viruses, protozoa, and these can be naturally occurring or introduced through pollution. And for our microorganisms, there are some key considerations. So the specific composition of dissolved substances varies greatly depending on the geographical location, the formation, and the human activity. And the concentration of these substances can impact water quality and the health of our aquatic ecosystem. Thank you for listening. This concludes my presentation on the nature of dissolved substances.
Thank you, Asia. Well done. Are there any questions? Anything jumps out at you, Mikey?
Yes, sir. So, first question. So the main solvent in nature is actually water.
Mm-hmm.
All right. So, sir, Asia mentioned like the taste of metal in the water, and what I've realized, especially when cultivating tilapias,
Mm-hmm.
they actually absorb, they take in that same dissolved metallic taste. So when you're actually eating them, you're actually tasting that metallic taste that is in the water. So if you drink the water have that metallic taste, and you're eating the fish and you're also getting that same taste. So it actually makes sense now. I finally find the connection why it is that the fish actually have that taste. Pretty interesting. Great presentation.
And it's not just the. All right, so let me just continue from where from what it is that you've just said. So, which is why lots of women don't want to eat the tilapias because of the hormone imbalance that it is believed to cause. But I will say not just the tilapias, other types of fish too will have the the sort of metallic sort of thing in it because of man's intervention and interruption of the environment. You have more cruises. You have the deposition of more mercury in the water, all of which are being absorbed by the fish, or let me not say by fish, but by aquatic life. So, whatsoever we consume there, the lobster, the crab, you name it, they are picking up more and more of these heavy metals that when we consume it, we can indirectly become, indirectly consuming these heavy metals as well. And as a result of that, we become sick because we have too many of these toxins, so to speak, in our system. Let us look at the polluted water. When we have the rubber tires and the plastic containers and the milk containers and the whole works, and these aquatic animals are nibbling on them, and the production of these. Is it because Asia kept referencing, for example, salt water? It, because of the bonding that takes place, it makes it reactive. So, for example, when I go to the supermarket and I buy my tin foods, and I don't particularly consume lots of tin food. The most that I do is really tuna, and I'm very particular with how it is that I once I open the tin, what it is that I do with it, because lots of time it is exposed to lots of heat. One, two, sometimes it is the can falls, it breaks, and the sodium benzoate as one of the preservatives in the food starts to react with the metal from the tin, and that's how we get food poisoning, incidentally. All right, and because it is that we're taking in the metal itself, not the tin, for argument's sake, becomes oxidized and forms new compounds, and then our body starts to reject the formation of these new compounds, and you may see little red bumps on you. You may start to have the white people them call it hives, and lots of these itching takes place. The swelling of the tongue takes place, and when the tongue starts to swell, it is very dangerous because you can actually swallow it. That now blocks your windpipe, and then you will suffocate. All right, so it's very, very important. One of the things that the chemical composition of what happens in the hydrosphere is very important, because the reactions that take place there, and then inadvertently you and I eating, preparing the fish and the eel and the crab and the stuff, when it is that they're consuming foods that are laden with mercury or other, heavy metals, it has an effect on us. Gallstone, for argument's sake, that is very excruciating. Don't want to know what it feels like. I hear it's excruciating. I can tell you what kidney stone feels like, and it is not very nice. But I gather that gallstone is even more severe than the kidney stone. And if I can tell you what kidney stone feels like, I don't want to tell you what gallstone is like. All right. So these are things that have these effects on our bodies, and we have to be very careful um, of what it is that we do. Some people decide that they're not eating any more fish. They don't eat fish because of these heavy metals. Lots more mercury are now in the ocean. And one of the things that I have to be careful of now, because I love tuna, is the mercury content in it. All right. And then if you want for your personal knowledge, you can go and research mercury poison.
Mercury poison is not a pretty sight.
Say it again.
I wish that on no one. It's not a pretty sight. I wish that on no one.
Oh, absolutely. Oh, absolutely. It is, you know, it talk about things like amnesia. Um, they talk about massive headaches. Um, it in pregnant women, if it is that she has, and which is why I'm saying to you, like the tilapias, lots of them don't eat freshwater fish, and especially if they're pregnant, because it can, you know, the cognitive development of their unborn child is something that is of concern to them. You talk about sleep deprivation. Um, it just pretty much just attack the central nervous system, and it's very dangerous, just very dangerous. And you know, as Michael, you said, and Asia spoke about it, the taste of this metallic taste, coming up, you know, um, based on the fish that we eat. Um, People become very nauseated as a result of that. We also have, and as I said, we have these gallstones that are being produced inside of you because the body doesn't use it, so it has to excrete it, and it so happens, God forbid, that it becomes these stones, and very excruciating, right? So terrible headaches. I know for one, from ever since I suffer from headaches. Yesterday after church, I had a wicked piece of headache, and I thought it was going to carry over into today, but thankfully it didn't, because I have a little antidote. I don't take tablets for it, because tablets for me, again, is one of those things that, um, though this is not environmental chemistry, but for me, for tablets, sometimes these tablets don't dissolve into your system, and it stays there. It stays there, and it stays there and develops into other things. And if you can think far and wide, you can figure out what other things I'm talking about. So I don't particularly take tabs. If I go to the doctor and get some stuff, I would more, if I can get the injectables, I would take the injection, because at least it gets directly into the bloodstream. Sometimes the coating of these tablets takes a while to dissolve, and the tablets actually don't dissolve, or it's not fully dissolvable, and it stays there and cause much more harm than it does good. So, it attacks the central nervous system, as I say, and it is very dangerous. That's all I can say to you. Um, you know, it part of the thing again, it causes for the skin, um, rashes, itching, um, and you don't want people to be looking out at you. And as a matter of fact, or to be scorning you, really. And I'm not sure if it is a contributor to skin cancers, because skin cancers now are prevalent now, than before. And I'm going to be moving into the atmosphere, come next class, or maybe towards the end of this session. I'll just give an overview of the atmosphere. And more and more people, I know someone, she has eventually died. I don't think it was a skin cancer that caused her death, but she was 90, was it 99 or 90, no, 90, over 95. She had a rash on her skin, and her children took her to the doctor, and it was skin skin cancer. And I was watching something recently when somebody else posted something to say, they saw this on their skin, and this is what it was causing, so forth and so on. They went, did a biopsy, and it came out to be skin cancer. And I have a solution or a cause of these um, cancers, and then you too will formulate your own cause and effect from the conversation that's we're going to be having. You also spoke Asia. I don't know if that clears it up, or if it adds to what it is that you're saying, um, Michael.
Yes, sir, definitely.
If you So Asia was speaking about the dissolved salts. Yes, we also had conversations about it whenever it rains, for argument's sake. You have you have um you have the calcium and magnesium ions that are being dissolved in the water and making the water hard. So yes, I agree with you on that, Asia. And the hard water, one of the things that we have to do sometimes is, all right, so let me read something here for you as it relates to hard water, because it is very important that we try to understand what is happening here. So it says, hard water is a nuisance in many areas. It is difficult to produce a lather with soap when using hard water. Instead, a white scum is produced, which collects the fibers of clothes and around the edges of sinks and baths. So, sometimes I have a friend who, you can't catch him bathe with bath soap. He only uses liquid soap. And I said, but why? I mean, it does the same thing. He say, yeah, it sure does. But we don't have the time for clean the bathroom ever so often because of the scum that is developed. So if you don't believe me, try it. Use bar soap, a bar of soap, um, to lather your rag, your washcloth, and see, after, by midweek, for argument's sake, you start this at the start of the week, and by midweek you can literally see the scum building up in your bath, as opposed to liquid soap. You don't have that sort of buildup, really. right? So this is what it is talking about in terms of the fibers of the clothes and around the edges of sinks and in the baths. The scum is due to the insoluble salts of calcium and magnesium formed with the reaction with soap, some of which is therefore removed from the solution. Hard waters also leads to the furring up of kettles, boilers, and pipes. So when you look at your water kettle, your kettle, but let me not use kettle. I so. I so. Let me go to
Yeah,
something that
use
is very
iron.
close to huh?
The iron.
Brother, let me go
Use,
something that is very close to my heart. So it's not the iron for me this time, but it's a steamer. So I use the steamer a lot because I use, sometimes, well, not sometimes, a few, time it's so hot now that I don't really want to wear some long shirts to work. So I wear polo shirts. So sometimes I wear lots of polo shirts. Now, I've had a situation where I was ironing my polo shirt and I recognized that the elasticity inside of the polo shirt went, and the polo shirt is like a dress. It just stretched out. And I was like, oh dear, this is not going to work. So I invested in a steamer. So it is that I can steam the shirt to get the wrinkles out so that I can do what it is that I need to do. Lo and behold, it worked for about a month and a half, 2 months. But of course, the teacher was using, and even though he knows, your teacher was using tap water. And every time I put the tap water in, I say, this thing is working pretty well. I mean, nothing happened until one day. Nothing coming out. And I was like, all right, so here now the little chemistry have to come into play. So I went into the kitchen, took a little bit of vinegar, dip it in some water, place the water in the reservoir, allowed it to steam up, and the steam started to come out. And I was like, yeah, I did it. And it started working. But erroneously, I was steaming something and left the vinegar water in there. And clearly, it reacted. The vinegar water is the acid. No, acetic acid. That's what vinegar is. Clearly, it reacted with the aluminum and caused corrosion. And because it now corrodes, it's all of those little holes that the steam would come through are now blocked up. So in order for me to restore that, I'll have to go and replace the whole of the inside there. And then I said to myself, I have nobody to be blamed but myself. I knew this and I should have done something better. So I went and got another one. But decided now that I'm going to be using deionized water, pretty much softening the water. So this is what we call it. So we have hard water, we have soft water. Go ahead.
You jump all the way over this still and go straight at the ionized.
Me say me go straight at the deionized, man, take out the whole of the something then. And for the second steamer, brother, it was working well for this one work a shorter time. Was working well for about 2 weeks. It's by the third week, it gone. And I said, this is it. I'm not buying anymore. Nope, nope. And then there was a change of heart. One came on Sunday of this week, and I still use the deionized water in there because clearly on the reservoir it says deionized water only. So far, this one is going, and it is going pretty well. So that's a soft water. Now, one of the other things that I could do with the soft water is use a little bit of rainwater, because the rainwater is also soft. Sometimes when you use rainwater for wash off, I know you can't wash off, don't.
Me to tell you.
You know,
As a country man.
I don't know if Asia know, but Asia, do you know if you spit in rainwater and put it on in there like you're sudding it up, it forms bully pasod? That's how rainwater is.
Yes, I tried that already, sir.
Yeah, man. So if you bathe with rainwater, all no you can wash off. So it's one of the things that I never liked doing at all. And especially when, you had water shortage and in hurricane and you had to be saving the rainwater and you bottle these rainwater and you had containers upon containers upon containers of rainwater and then you have to go and pour out some rainwater to wash off. It don't make sense. And worse if you use
Yeah,
Dove
what?
soap with it.
Yeah, because if you are washing a sir, you soak up your clothes. Yeah,
Mhm.
one time, you was rinse out them the clothes.
Absolutely,
Well.
absolutely. And then no, so and then it speaks about like the limestone, the calcium carbonate plus the water. Um, you're going to get the calcium ions coming off, the Ca2 plus, the cation coming off, the Ca2 plus. And if you do like dolomite is a calcium carbonate, magnesium carbonate combination. And then you can have the calcium ions coming off and the magnesium ions coming off, right? Those are things that make the water hard. So it says the removal of calcium ions and the magnesium ions as insoluble precipitates can be achieved by boiling the water. No, for example, so I personally cannot drink tap water. I personally cannot drink it. Um, so one of the things that I do is I used to boil my water until I started going to bottled water. So in order for you to remove these heavy salts, the calcium ions and the magnesium ions, you can actually boil the water, um, pretty much reversing it so that the water now becomes soft. Right? I am not writing notes and I can't show you the equations, but for sure, on one of God's willing, I can show you what those equations look like. Um, one of the things that I can do is what I just spoke to you about, using the ion exchange resin. So one of the things that I've been doing in the lab is we have a resin and we connect the resin to the water tap. And the water runs through this resin and we have an outlet tap. And that outlet tap now will produce deionized water. So it's an ion exchange. So what happens is that um, it from the hard water, it pretty much takes out the calcium ions and because it creates reactions in there and it also takes out the magnesium ions. So we have pretty much soft water. So when I use the water that is coming from the ion exchange resin, and this is how they do your deionized water. In my steamer, I shouldn't be having the challenges that I had. I really shouldn't, because it is that I don't have any of those elements that make the water hard. Now, lots of people, when they see the white stuff in the kettle, they call it chlorine, but really it isn't chlorine. It is your calcium salts and your magnesium salts. And more of these salts are the carbonates. So when we boil it, we're getting the carbon dioxide coming off because what it is that we're using is some vinegar. And the vinegar now in the from the acetic acid, it's causing the it's causing the it's facilitating the reaction. And the reaction with the carbonate and the acid is when they give you a salt, carbon dioxide, and water. So dissolving, it's really dissolving the salts in such a way that when you look at it now, what is going to happen is it is something that is yeah, have you ever boiled water and you see a film of white stuff on top of the water?
Yes, sir.
Yeah, man. So when I boil water, I don't want to drink those stuff because when you drink those stuff, these are precipitates of the salts that come out. which is a precipitate of the calcium and the magnesium ions coming out, right? And this is what gets into our kidneys, and this is what now forms kidney stones. Real talk. And trust me, been there, done that.
We don't want that one later. We don't want the stone at all.
Wicked piece of something that. Wicked. All right. So we really don't want that to happen to us. So that's exactly what is happening right there. Um. So so for me when I boil my water, I use like a cheesecloth to strain it. And when you strain it, you can feel the grains of the salts that are produced that would have inadvertently get into your system. That is really not good for you. Right? So there are so many things in the environment, from the hydrosphere that we have to use that cause us to become sick in one instance, cause us to be, we may think that we're doing something good for the body, but really and truly we're causing more harm to the body. So some people say that, oh, when we're eating fish, for argument's sake, when we're eating fish, the fish is very good for us. But really and truly, if we're eating fish, but the fish has a high source of mercury, can that be good for us? No. If we're drinking lots of water, but the water has lots of these calcium and magnesium ions in it, is it good for us? No. So we have to take things in moderation. And the other thing is, when we drink purified water, I don't want to call them name now because I'm being recorded, but when you go to these water companies, and you know them because them sell the bottled water all over the place. When we have the bottled water and buy the bottle,
We call him here.
you know what the man them do? It's the same thing like what I call the resin. The man them run it through, the man them remove every mineral from the stuff. Treat it with ozone, and ozone incidentally is O3. And the ozone is to purify the water. So anything that is inside here, so that will cause us to be sick, the water is purified, and then they go and add their stuff to it. So sometimes when you drink the water and it tastes a little salty, you can say, yep, too much salt going to this water. So they remove everything and put back what it is that they think you need. That can't be right. So, you drink it like, no, we can see which one it is that I have here. Okay, right. So no, this one is Price Smart purified drinking water with added minerals. If any one of you have the bottle of it, now it says with added minerals. And let me read on here. So it says ingredients. I may say ingredients, sir. Bottled water, yeah man. Purified water, sodium chloride, magnesium sulfate, potassium chloride, a negligible amount of sodium and minerals added for taste. For taste. So they are taking out everything out of it, putting in what proportion they feel they're supposed to put in, adding sodium chloride to it. So even when you're drinking your bottled water, you're having more of these salts that some people not supposed to be having in the first place. Nothing like getting spring water. That's the point I'm making. Natural. The proportion of the minerals in there is to T, because what the man them do, is do their own research to find out how much of this mineral is inside there, how much of that mineral in there, and then approximates it, and then add that approximate amount of mineral now to the purified water. But the truth is, most times it's purified water we get because the spring water costs more, and the purified water is cheaper. So most times when we go and buy a bottle of water, it's purified water we pick up, as opposed to be taking up the lifespan or the Catherine's Peak, which is spring. Any comments? No comments? All right. So you spoke about the hardness of the water. There was something else that you spoke about that you said something about something sinking and um something sinking Asia, and you reference to the to soda. What was it? You remember?
I think it was an analogy I gave. Which one again? I think it was the. I mean, I'm going back to the presentation.
Yeah. If you can't find it, it's fine because I have a notation. I was trying to find my actual notation to speak
Oh, and the
about
one
it.
with the soda, sir.
Yes, the one with the soda.
Um, the dissolved gas is one I think where I said where the gas molecule squeeze in between the water molecule, and when it gets warm, the molecules move faster and then escape.
And when it is
Something like
cold,
that.
it sinks to the bottom, right?
Mm-hmm.
Okay, so that's exactly what happens in the hydrosphere. So when the dissolved carbon dioxide, when it's cold, it sinks to the bottom of the hydrosphere in the oceans, and depleting the level of oxygen. Right. So when I get to the atmosphere, again, Asia, you'll hear me speak about that because it also happens. So, sometimes them say, let me ask you the question. Can a fish drown? Hello, somebody?
Yes, definitely.
How so?
Yes, it would be
Um,
thrown in water.
so we're
Who?
answering Mother Joe.
What was that, Asia?
I would say it's not like us drowning in water. It'd be like more like suffocation.
Oh,
So if they don't get enough oxygen or so like that, they can suffocate. They can
and it's based on what you presented just now in terms of the
with the
cold dissolved. Go ahead.
aquatic animals. So just like in the
Right.
presentation, where you said the dissolved oxygen in the water helps fish to breathe and so.
Absolutely. So if you don't have enough, so when the cold when the cold when the cold when the cold carbon dioxide falls sinks to the bottom of the ocean, what happens is they what happens is you have more carbon dioxide down there, you have less oxygen. Having less oxygen, it means that aquatic plants and animals down there cannot photosynthesize. They cannot photosynthesize, so it means that they cannot produce any oxygen. So you don't have any production of oxygen taking place right there. You follow what I'm saying?
Yes, sir.
Yeah, man, because you have more carbon dioxide down there. So during sunlight, you're not going to have any, we have any photosynthesis there taking place. So what it is that you're going to be having is more carbon dioxide being produced. So therefore, aquatic plants and animals down that side are going to die. They will die because they cannot survive in those conditions. So yes, the fish them can drown. And this is how you have things like barnacles, and you have things like the shell, seashell are formed because they have the massive level of carbon dioxide that precipitates out in water. So literally, you can have the carbon. So because it is so heavily carbon, it is so heavy in terms of having that much carbon dioxide to precipitate carbon. If you get to that section of the that you're having, you walk in the ocean, but you're walking in dust and suffocation from shells. They sometimes the one read on how these shells or shells are formed in the ocean. It is the precipitation of these carbonates.
Sorry, the internet's not stable. You're breaking up really bad.
No, I thought it was mine.
All right. So what I want you to do, I'm gonna send you some stuff. I'm gonna stop here for today. I'm gonna send you some stuff that I want you to just read on. You guys did pretty well for the hydrosphere. I'm going to be collecting those, so it is that I can collate and send out to everybody so that everybody can have an idea of what the other persons did. And then know what I want you to do. I want you to start reading about the atmosphere. The atmosphere has several layers. The troposphere, the stratosphere, the mesosphere, and the thermosphere. So there are 4 spheres in the atmosphere that I want you to read upon, just to get some idea. So it is that when we come to class on Tuesday, I believe it is, we can have a more fulsome conversation. Fair enough?
Yes, sir.
All right. So
Yes,
big up on yourself.
sir.
I end here tonight.
All right, no problem, sir.
All right, cool.
Oh, sir.
God.
Sir, got it. All right. All right, here you go.